right, hey, welcome to lecture 23, Quantum Physics for Non-Physicists, and today is the 3rd of December. And thank you also for joining the presentation by Cesar just before this. So now you know that if you thought my analogy is so wild, it's wilder out there. Okay, so we will continue today with quantum thermodynamics, and now we'll go back to this problem of wanting to erase a qubit. So some qubit that could be in some fully mixed state, and we want to take it to state 0. And our analogy today was brought to us by Rob Speckens, who is a researcher in quantum foundations and quantum reference frames and thermodynamics, which is about like what is actually costing work in this whole quantum computation. Like, where do we need to erase something? Is it like the measurement itself that costs work? Or is it just preparing an ancilla for implementing the measurement that costs work, for example? And it just, because there's been some debate about this in the community for a while, for a year or two, he just compared this to the idea of like, if you're driving a car, what's actually costing? Is it like while you're driving that you're consuming fuel, or do you only count it at the end of the day when you go and have to refuel and have to pay for this fuel here? Right? It's the same idea, right? No matter how we model a quantum measurement, at some point, we know that we are creating entanglement between two systems, which means that if we look at one of them locally, it's going to be very mixed, which means that if we want to then use these qubits again for something else, we'll have to erase them. And it doesn't matter if we're counting whether that we are erasing them at the beginning before we start the computation, or if we do it at the end. Okay, it's a very light analogy today. So let's just recap what we've done in the last lecture. So we looked finally at what a quantum thermal state is. So we saw that the density operator depends on both the Hamiltonian and the temperature in this way, and it's given by this exponential distribution over the energy eigenstate, where the exponent depends on the inverse of the temperature, in this case, just a positive constant, right? And there was this normalization factor just so that the whole thing gets trace 1. And this is called the partition function. And then we saw if we compare, for example, a hot system and a cold system, the difference between them is that the hot system will have higher probability of being in an excited state, right? Because this t larger, so 1 over t is smaller, so minus 1 over t is larger. So we're more likely to find an excited state, whereas the cold system will be more likely to be closer to the ground state, right? So in particular, if you look at the average energy, to be higher in the hot system than in the cold system. Incidentally, this is why something that Cesar referred to today, which was that we always want to cool down quantum computers. It's because we want them to be very close to the ground state, which then we can manipulate to be, for example, the 0 of our quantum computation, right? Or either the 0 or the 1. Okay, good. Then we looked a bit about applications of this, what we can do with this thermal state, and we looked at 2 in particular. One was the fridge, and the other one was a heat engine. And both had kind of the same construction inside, right? So we had a cold qubit, a hot qubit, and some target system. For the fridge, this target system could be a qubit, and what was important is that in order to have conservation of energy, you need these energy gaps of the 2 smaller ones to add up to the larger one. Okay, so that's this condition here. Now, if we wanted to work as a fridge, then we needed this temperature of this second smaller gap to be larger. So this to be the hot one, and the one with the wider energy gap to be the cold one. And then what was the interaction that we turned on? So this was something that simply favored a transition, and this is a transition between the state 0, 1, 0, and then 1, 0, 1, right? So we have this term here, red, corresponds to this direction, so the target gets excited, the cold goes down, cools down, and the hot gets hotter. And the green one was the opposite, so the hot gets colder, the cold gets hotter, and the target also gets colder, right? And then we saw, well, depending on if we fix these temperatures, then we can engineer the size of these gaps. such that if we satisfy this condition, then it means that the initial state is more likely to be this than this, right? Which means that the green transition is favored. So over time, what will happen is that like this kind of green direction is favored, which means that over time we kind of cool down the system. And this energy to cooling down the system comes precisely from the energy of the hot bath minus some energy that goes into the cold bath. So this is like a mini fridge. And one application of this, you could think of, well, your target being the inside of a quantum computer, and you want to keep this environment very cool. So what you do is to connect it to a cold and a hot qubit in this kind of way, right? So this would be not like your main quantum processor, but something adjacent to it to try to keep it cool. Good. Then the other example we saw was just the reverse. So it was exactly the same transition now, except that now this was the hot and this was the cold, okay? Which meant that these ratios here are reversed, which meant that the red transition is favored. But of course, we don't normally want to just heat up some random system, but what we might want to do is to heat up a battery. So to increase the energy in a battery. So then instead of just having one qubit here with energy gap E1, we have like a ladder where the difference between two levels is always E1, right? And we saw that kind of with the same interaction, except that now we need to sum over all EI. So before this was just 1, 0, 0, 1, but now we just go from EI to EI plus 1, right? And then what was the condition here for the red to be more favored than the green one? It was that the population of this state had to be larger than the population of this state. So this in turn results in this condition. Okay, so we want this number to be larger than this. But then again, if we want the engine to be maximally efficient, then we want them to be very, very close, to be like almost identical. So just slightly tipped in the direction that favors the battery going up. So if we have this, then we computed the efficiency of such an engine, and we saw that it corresponded exactly like in the classical optimal case for reversible engines, the temperature of the hot bath minus the temperature of the cold divided by the temperature of the hot. Right? So we saw that there's no trade-off between size of a heat engine and its efficiency, even though it's going to be very, very slow, but it doesn't leak more than a large classical engine. Good. So these were examples of kind of autonomous engines where we just turn on this interaction and let it run. Now we're going to look at something that is not autonomous. So we're actually going to have to go there and turn some knobs, which means instead of having interaction Hamiltonian, we're going to have to apply a series of gates, U1, U2, U3, and so on. And this was this example that motivated us starting into looking into quantum thermodynamics in the first place. So what was this? This was the idea of erasing a qubit, right? So say at the end of the computation, we have a qubit that is in a fully mixed state, and it degenerates in the simplest case. We have our battery, and maybe you have access to a heat bath of some form. And then we want to apply some unitary that commutes with the total Hamiltonian, so it doesn't bring us any new energy, such that at the end of the day, we want to have this qubit ready to be used again, so again in the zero state. We know that we'll have to pay some price here in the energy, so maybe in analogy to the classical case, maybe you expect it to lose energy kT log 2. Okay, so this was the result we got from the classical case, but there's no guarantee that it will be the same in the quantum case. And we want kind of the heat bath to stay more or less the same, right? Because it's a heat bath. Okay, of course, in reality, the final state will not be exactly this very neat product state between the three systems. There will be some correlations because no like finite sized engine is going to be perfect. However, we'll do quite well still. Okay, so now finally we have the tools to kind of look into this heat path. So we know what a thermal state looks like, but now we need still to define what the Hamiltonian is that we're going to use. And in this case, it's going to be kind of a very standard, well, let's not call it standard Hamiltonian, but it's going to be saying that, well, I could put whatever Hamiltonian I want here, it's always going to thermalize. That's my idea of like having an atmosphere at some temperature. So what I'm going to do is to take a bunch of qubits, so n+1 qubits, where each of them has an energy gap that like is slightly larger than the previous one. We'll make this precise a bit later. And if I take a thermal state on the total thing, like we saw, this is equal to the sum of the thermal states for each of these individual systems. Okay, if the Hamiltonian is just the sum of the Hamiltonians of individual qubits, okay? Which means that we'll have, for the first one, we'll have the thermal state of this Hamiltonian 0 at temperature T. For the second one, we'll have the thermal state of Hamiltonian 1 at temperature T, Hamiltonian 2 at temperature T, and so on. The key thing is that they're all at the same temperature. And of course, as we increase the gap, if the temperature is the same, then the probability that they are in the excited state is going to be smaller and smaller. Good, so let's try to make this a little bit more precise now. Okay, so I think in this case, I don't even need the first qubit, but let's just write it anyway. We don't lose anything. So what we take from the heat path, we take, say, n+1 qubits. So from L equals 0 to n, hi, where each of these hi's, this is a qubit. Okay, so it's a span of 0 for L and 1 for qubit L. Good. And what's the Hamiltonian of the heat path? It's going to be a sum of local Hamiltonians. And what I mean by this is that each edge L is going to act only on the qubit L and is going to act like the identity in the rest. Okay, of course, this rest depends on L, so these are all the other n-1 qubits. Okay, so depend for each term. Where what we want here, well, we want this HL to increase with L, right? So it's going to be d delta times the number L, and now this cube, the excited state, right? So the energy of the excited state is always going to be L times delta. Okay, so it will increase with L. And how do we choose this delta? Well, with our battery, right? And our battery looked something like this. Okay. Whereas here we just say that we just choose these deltas to be the same. Okay, so we pick here sum over k. And let's say for simplicity, we start, it's an infinite ladder in both directions of delta times k. Okay. Right. Now note that this is not physical to have a system with a Hamiltonian going to minus infinity. So in the real world, when we actually take a real battery, we'll bound it. We'll also bound it on the top in both directions, but it's really important to bound it at the bottom. But for this example that we'll see, we don't need to consider it. So in real world, we will bind this. And the way we'll do for the analysis to be the same is just say, well, maybe it's bound at top at the bottom, but we'll start with some state here in the middle, such that it never gets close to the top or the bottom in our protocol. Otherwise, it just gets a bit more messy because then you start kind of accumulating stuff at the bottom. But don't worry about this for now. So these finite size effects. So what is the interaction that we want? Actually, it's going to be very, very similar to this interaction of the heat engine. So what we'll do is to, at every step, the process will have n steps, or yes, n steps. And at every step, we're going to take one of the qubits from the path, and we're going to apply a joint operation on the battery, our system, our qubit system of interest, and this qubit from the heat path. Okay, and we'll see that this works. So let me just show you what the interaction is that we want. So let me just say that we're going to apply kind of un minus 1 u2 u1, where each of them is going to act in a very special way. So let's take here our battery again. And we take our qubit S. So this is S, this is the battery, and we're going to take one qubit, I don't know, L, from the bath. Okay. And what our interaction will do is to just transform between two states. So let me just write it. First, I'll just write kind of a pseudocode for this. So it's going to be from I on the battery, 0 on the system, 1 in qubit L, and EI plus 1, 1, 0. Sorry, EI plus L. Okay, so let's see what this means. So let me just draw here the initial occupations of these two things. So let's say we are somewhere in the middle of the process. Maybe this qubit is not uniformly mixed anymore. Maybe it's like somewhere a little bias here. Okay. Okay, and what this does is to take from 0L, 1 on the system. This one goes there. This one goes there. And because I went up in this thermal qubit, I need to go down here. By how much? Well, for this to be energy conserving, if I go up by L delta, right? That's this. This is kind of L delta, this energy gap. Then I need to go down here by L delta as well, right? So in this case, it's this. It's L delta. Okay, so it will go down from any initial state. It needs to go down by this amount. What's the other direction? The other direction is going from 1 in L and from 0 here. And then because I went down by L delta, I'm allowed to go up by L delta, right? So that's it's kind of this. Okay, so in this case, L equals 4, I think. Right? And so on. Okay, and it does this for any initial state of the battery. So what is the idea here? The idea is that if the, let me just write the other states here. 0 in the system. So in green is like the initial state for the green transition, and in red is the initial state for the red transition. So good. So what we have, the idea is that if we choose, we're going to choose this L at any time on the protocol such that one of them is going to be more likely than the other. So for example, if we want to erase the system, so we want to do, let me go back. If we want to do this direction, right? So we expect the battery to go down, but we want to go from a more mixed to a more pure and closer to the 0 state here. So we're going to choose it. We're going to choose this qubit such that the red transition is more likely. So it goes down here, but it kind of pushes the system S closer to the 0 state. Okay, so it's the equivalent of kind of cooling this system, but of course it's degenerate, so it's not cooling. Okay, and so it's like the energy goes from the battery to the heat bath, kind of mediated by this system here. If, on the other hand, I'm trying to go in the other direction, this is also possible. So imagine I have a bunch of like pure qubits, and I want to extract energy from them. This is possible. So this is the idea of extracting work from just information. Okay, so then I want to make this a bit more mixed and raise the energy of the battery. Okay, so then I'm more in this regime of the heat engine, but with one of the qubits being degenerate. Then I want to engineer things such that the green is more likely. So I just pick a gap here such that the probability of the initial state being the green one is more likely than being the red. So then I go in this direction up. Okay. So before we do an analysis of this, which you'll do more carefully in the tutorial, first we need to just take this intuition and write it as a unitary interaction, right? So what we want is it's a U global, and this is going to be the U global L. So first, as per usual, we have the sum over all states of the battery. So right now it goes from minus infinity to plus infinity. And then what we need to have the green transition. So the green transition starts from this green initial state. So from, EK, let's put K. From EK, 0, 1, battery S, L, and goes to, EK plus L, 1, 0, right? LS battery. Plus the other direction, so that's just the opposite. So that's EK on the battery, 0 on the system, 1 on L is the final state, and the initial state was EK plus L, 1, 0, battery S, L. Now, if I want this to be a global, then I need to say what it does in the rest, so it does nothing. Where here rest is the other thermal qubit. Now this is kind of the form of the Hamiltonian, not of the unitary. To make it a unitary, I need to add the terms. I need to tell it what to do if the initial state is, for example, 0, 0, or if the initial state here is 1, 1. Okay, so in that case, I don't want to do anything. So this would be identity in the battery, do nothing, times 0, 0 on L. Also, don't change them. On S and L. And if it's 1, also don't change them. And again, do nothing in the rest again. So just put S, L, S, L. Okay. So this is going to be our global unitary, and we're going to do explicitly one step here. So in the tutorial, you'll just show that indeed this commutes with the global Hamiltonian. Okay, what's the global Hamiltonian? So it's again, it's this ladder for the battery, nothing on the qubit, and then all this bath qubits, okay, with different energy gaps. So you'll see that this is allowed, which you can see here directly from the fact that it's energy conserving, right? What you gain here, you lose there, and vice versa. Okay. So now let's do this. Let's do the first one. Okay, so let's do here the first one, and we'll see what's happening a little bit, and then in the tutorial we'll see what will happen when you do all of them. Okay, because then you need to see what happens here in the battery and what's the final distribution of work. Incidentally, what will happen is kind of a random walk, which we've learned about today. So let's take the first interaction, so U1. So what's the initial state in this case? So let's say that the battery starts at some state E0, for example. The battery. Okay, so right in the middle. And then in the qubit, we said we had a fully mixed state. And then we take the first qubit from the bath, right? So that's tau of H1 and temperature T. So let's just draw all these things first. So here we have chuk, 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 chuk. There we have chuk, chuk, battery system. And here we have L being like this. Okay. Where this is fully mixed. And here there's a slight bias towards the zero state, right? But it's not a large bias because this gap is very small. And here, let's say we start with 0. E0. Okay, good. So now, let's just write this. Let's just write what this is. So this is 1 over Z. And then Z of H1 and T. And then it's going to be 0, 0 plus E2 minus K over T delta, right? Because this gap here is just delta, this L equals 1. So 1, 1. So now let's write, we don't care much what's happening in the first system, because what we need to know whether the red or the white transition or the green transitions are more likely is just what's happening in S and in this thermal qubit. Okay, so we have with probability 1 over 2 and now this Z. And then what we have, so we have on the system 0, 0 S plus 1, 1, right? The 1 over 2 is already here. And then here we have 0, 0 plus E2 minus K over T delta. So this number is smaller than 1, right? That's what's important here. Good. So this gives us what? 1 over 2z. And now we have 0, 0. Okay. So that's this term with this. Now let's do this and this, because this is the other term that we don't care about. So plus 1, 1, 1, 1 times E2 minus K over T delta. And now come the interesting state. So what was the red one? The red is kind of what we want. That's 1, 0. One, 0 is this and this. It has no coefficient there, plus the 0, 1. This has an interesting coefficient. E2 minus K over T delta 0, 1, 1, 0. Okay. Where here, I'll just write the subscripts in the relevant terms. So this is S and this is qubit 1. S and 1. S and 1. Right? So now we can act. We can act with the Hamiltonian on this state. So the total state is this times that. And just to give you an idea of what will happen, so this coefficient 1 here is larger than the coefficient there. Okay, which means that the red transition is favored over the green one. That's row 0, we call it. So when we act with U1 on row 0, U on dagger, what happens? Well, we're going to do it extensively for this one, and then we'll see. We'll see for the other one. Okay, so first of all, we know that nothing will happen to this coefficient. We can just put it at the beginning. It's just a number. Then we have this is 0 on the battery. That's what started. Okay. Tensor this thing. Yep. Okay. And now we plug in U. Now U is very large, but luckily not much will happen. Oop. Except mess up. Okay. And it's better to put some extra brackets in places. So there we go. And now we need to do the complex conjugate here. And the complex conjugate turns out to have exactly the same form. Except I can just change the colors to keep it up to date. So this is the complex, yeah, so this is the transpose conjugate of this term. That's why it stays in red. And this is a transpose conjugate of the other term, of the green term. So let's make it green. Okay. Good. So let's start to mess with this. First of all, this sum over case now doesn't matter much, because the only term that will survive is the one where we have E0 here, right? Everything else will go away. So okay. Now, the other thing you have to see when you look at this is that this term will do nothing to this, so we'll just keep it as it is, and the same will happen here, right? So this thing is going to survive as it is with the same E0 there. Let me write it then. So resize to make it a bit smaller. Okay. So it's going to be 1 over 2z. And now let's first write the terms that survive here. So we have the E0, E0, and then this, I'll just write it like this, so 0, 0. Right, and sorry, here I'm omitting all the other qubits, otherwise I'd have to write the initial state for all the qubits, all the thermal qubits, and I'm not doing this yet. Okay. Good, so plus 1, 1, 1, 1, and this at this factor E minus K over T delta, right? So this survives, plus, so what happened to the green terms? So when this green hits here, it takes this E0 to E1, right? Because it takes EK to EK plus L, and there's only 0 here. But then the only thing that survives on this side will be this thing here. So where we have this inner product 0, 0, 1, 1, that's 1. But of course, then they will change now to 1, 0. So let me write it here. So it is going to be E1, E1, tensor, now 1, 0, 1, 0. Okay. And what was the factor behind the green thing was E2 minus K over T delta. Plus, the term that will survive is here when we have red on both sides. Okay, so by the way, if you have red and so green and red, then it will not survive because they, this acts on EK, but this acts on EK plus L. It's not gonna work out. Well, not because of this actually, because this doesn't matter because the sum goes over all EKs, but this acts on 0, 1, and this acts on 1, 0, and all of these terms here, they are diagonal, right? So only when they are the same, both on the left and on the right, will the term survive. Okay. So no, this was the green term, and now the red term. Well, the red term kind of lowers this energy here, right? So remember L equals 1. So it goes to E minus 1, E minus 1 times, and here it swaps this 2. Okay. Good, and that's it. So the other qubits, this acted as the identity on the other qubit, so nothing changed. And we don't worry about them for now, we just take one qubit from the path at a time. So what can we see that happened here? Well, first of all, if we now look, let's look now at the reduced states in the 3 systems. Okay. So if I look just the row of the battery 1, This is going to be what? Here, these two are diagonal, so they behave very, very well for the partial trace. I just need to take this thing here plus the coefficients. So it's going to be 1 over 2z. And let's call this z1 because it's the z of the first qubit. Okay. z1 times this coefficient, e2 minus k delta over t, and was is 0. Okay, which you can interpret as with this probability, nothing changed, plus the other two terms. So the green was with probability 2 z1, and this thing, e2 minus k delta t, it increased a bit. Okay. And with probability just 1 over 2 z1, it decreased a bit. But what's relevant here is that this, oh, sorry. Is that this probability here is larger than this, right? So the probability that it goes down is larger than the probability that it goes up. I think this factor of 2 here is too much. Yeah, it is too much because you have, we have two terms here. So sorry about that. The correct answer is to this. Okay. So if I write this, and this was the initial state 0, then with a smaller probability it's gone up, and with a larger probability it's gone down. But it's still more likely to be there. So that's what we mean. It's like it's kind of a random walk, but that's tipped to go down. Like the average energy is now a little bit lower. What is happening to the qubit on the other hand? Or qubit of interest, so OS after time 1. Okay. So now in which states was it? In which states was it 0? So here it's 0. Oh, this should be 0, 1 here. Okay. So here it's 0 and there it's 0. Okay, so the overall probability, it's going to be 1 from here plus 1 from here. So it's going to be 1 over 2 z1 times 2. Yeah. Plus 1 over 2 z1. What are the contributions for 1? So you can do this explicitly in the tutorial. Don't worry about this. So the contributions where he has 1 are these 2. Both of them have this weight here. So 2 times e minus delta k over t 1. Okay. Which is what? Well, this is, if you look at it, so this is exactly a thermal distribution, right? 1 over z times this plus this was like the population that we had in the thermal state at the beginning, right? So this is exactly the row of the first qubit before we did this step. Okay. So it's exactly this state. So what this operation did was to kind of swap these two states. So if we computed the final state in here, it will be fully mixed. So we swap these two. And the difference in energy, because of course this is a generate state, got eaten up by the battery. And then we do the next step, right? When you do the next step now, let me take just one more minute. So now we do second interaction. So with U2. So now we have our qubit here that is now slightly more biased towards 0. And now we take one that has a slightly larger gap. Okay. So the idea is that we always take a qubit from the thermal bath that is a little bit more pure, a little bit closer to the ground state than the qubit that we want to erase. Yeah. And we perform this operation again. So now when we perform the operation again, we can put here all the calculations again. Of course, the initial state is going to be different. This is what you'll do in the tutorial. And in the end, this the energy here in the battery is going to be even more biased down, but with a little bit of spread. But your qubit S is going to be a bit more pure. So we do this many, many times. When you get to the last qubit from the bath, then you're going to have, so let's see, UN. Now we're going to have here, well, this being almost pure, right? We'll never really reach a pure one. And there we're going to get even more pure in the thermal state from the qubit. And after that, so in this case, the jump in the battery is going to be very large, but it will happen with very, very small probability. So it almost doesn't happen, right? And after doing this again, then it's kind of most of this weight is going to be moved to the 0 state. So throughout this process, we always kind of increase the energy of the bath a little bit. We decrease the energy of the battery, and we cool this, well, we erase this qubit to be in the 0 state. We will do this explicitly in the tutorial so that you can see it happen. But the idea is that we can indeed have this kind of process where at the end, this will never be a product state exactly. There will be correlations created with the bath. The bath will be a little bit hotter than it started with, but under these assumptions that we always look at, like the bath is much, much larger, and we have many, many, many of these steps, then the energy leaks to the bath will not be very, very large. That's the idea. And so this is a way where we can transform between kind of one resource, which is information about this qubit, as opposed to entropy, that's what we have here, and another resource that's energy in our battery. Okay? And you'll see that this spread here is not significant compared to the energy gain or loss. Okay? In fact, you'll see that it will depend on the number of steps that we do. Okay, very good. So this was it for this part of like intuitions about quantum thermodynamics. And now in the next lecture, what we'll do is talk about the, how to model these couplings to a heat bath and how to model open systems. And then that will be it for thermodynamics for now, for this course. Okay, very good then. See you next time.